Congratulations! You've just been hired as a city planner in your first job, planning an airport. And that means planning the terminals, knowing the wind patterns so you can angle the runways correctly, and finding the length of the runway. Wait, finding the length of the runway? How do we do that? Well, that will require a bit of calculus and physics. Before we go over airplane takeoff mechanics, we need to understand some calculus. For those who know their calculus, you can skip to the time indicated on the screen. What algebra focuses on is the big picture of a graph. For example, you may have been asked on your algebra exam to plot the general shape of a graph with some specific points on a graph, or asked about the end behavior or the key points along a graph. What calculus focuses on is the extremely small sections of a graph, and more specifically small changes in a graph, or what is happening in the small slit. With that in mind, here's a quick rundown of calculus. This is a limit, essentially what an output approaches when an input approaches some number. The bottom portion is what the variable approaches, and a function what the dependent function approaches as the bottom approaches the desired value. In this case, when this graph approaches 1, the graph output approaches 1. We can think about having blockers to the immediate left and to the right of the point to limit our scope into thinking about the specific point. A good idea of remembering what a limit is the fact that 0.999 repeating is equal to 1. Here's a common proof. The way to prove it is as follows. The limit way to quote-unquote prove this is as follows. Logically, if number x and y are the same thing, then they should have a difference of 0. When you do 1 minus 0.9999 repeating, your answer is an infinite amount of zeros and then a 1. It can be written in a pseudo-mathematical notation as follows. But this number has so many zeros that this number approaches and is basically 0, and thus 0.99999 is equal to 1 because the difference between these numbers is basically 0 if not exactly 0. Note, I'll be using the word error throughout the calculus concepts. Error just refers to the difference between the actual point and the estimated point. As we look at the previous slide, if the difference between two numbers approaches 0, then the numbers are the same. Thus, if the error approaches 0, the estimation becomes better and better. Derivative is the rate of change at a very specific moment on the graph. This seems pretty abstract, so a real-life example is that the derivative of velocity is the instantaneous acceleration, because instantaneous acceleration is the rate of change of velocity at any moment. The derivative can be written as dy over dx. What this can be interpreted as is the change of y over the change in x, where the change in x approaches 0. It's pretty standard for the dy dx to be written as a function of x or y, in which case the derivative changes as x changes, or as a function of x and y, in which case the slope depends on the point it is at. As you might notice from the graph, for areas near our point of tangency, the line is really close to our graph, meaning it has very low error. This is an extremely zoomed up version of the last graph, and the largest area of these arrows is maybe 1/10 of a box, or small compared to the rest of the graph. You'll notice that the shorter change in x there is, the smaller the error is. The tangent line could, in theory, predict or estimate the values of the graph. What I mean by that is that if you all of a sudden had half of your graph completely missing, you could predict the corresponding y values at an x value a relatively short distance away from the point of tangency. This is called linearization. At point 0, -2, we have slope -19 over 10. And let's say we wanted to predict the corresponding y value at x equals 0.1. Reasonably, if we didn't know the algebraic function of the graph, we could set up a linear function in the point slope form y plus 2 equals -19 over 10x. Remember, we have a slope of -19, 10 and a point of 0, -2, and thus we can set up a point slope formula like this. And we can predict that at x equals 0.1, we have a y value of negative 219 over 100, or negative 2.19. There is obviously an margin for error, but that margin of error is quite minimal when the limit of the change of x approaches 0. Now, if our x step is like 0.1 or even smaller, then we barely have moved along our graph, and we might be trying to estimate a point far off to the right. How do we get a relatively accurate estimation for the point of a larger x? The answer is the repeated use of linearization, or better known as Euler's method. Let's say our dy slash dx is x times y and our starting point is 0, 1, and the step length along the x-axis is 0.1. We can keep linearizing until we get to our desired x value. Let's say x equals 2. Our actual value is supposed to be the square root of e. I ran some Python codes, and our estimated value with step length of 0.1 is 1.701, with an error of 3%. Now we did it with a smaller step like 0.01, our error would be 0.3%. Knowing that decreasing our x step distance will decrease our error will be helpful later. And this is the comparison of the estimations to the actual graph. Our next bit of calculus is integration, more specifically definite integration. Graphically, definite integration is the area under a graph from a left bound A to a right bound B. Analytically, integration is just the opposite of a derivative. With the example of velocity and acceleration, the integral of an instantaneous acceleration from time t equals 1 to time t equals 2 is just the change in velocity from those times. For example, in this graph, the difference of velocity from time t equals 1 to time t equals 2 is just 15 meters per second. And thus, the integration of acceleration from 1 to 2 is just 15 meters per second. Now, without knowing how to integrate, and with curvature where the area is hard to find, we will need to approximate our area. One such approximation method is the Riemann approximation method. The Riemann approximation method is taking points on a graph at a consistent interval and making rectangles or trapezoids under the graph. For the most accurate approximations, we will be using a trapezoidal approximation. A trapezoidal approximation takes the front end and the back end of an interval and makes a trapezoid with the x-axis. The area for each trapezoid is x2 minus x1 times y1 plus y2 divided by 2. The regions in red show you the slight error we get. The error is definitely small, but you want to get a more precise answer. If we decrease our intervals, our trapezoidal approximations with the graph become better. For example, compare the original approximation of step 0.125 to a new approximation of step 1. In general, we want all areas to be estimated decently, with no specific area having severe under or overestimations. Okay, now that we know all of our calculus, let's get on with physics. Once again, if you already know your flight physics, feel free to skip to the time displayed on the screen. For an airplane, there are 4 key forces: the thrust from the engines, the lift from the wings, the drag from the wings, and the downward force of the weight of the plane. Thrust is just the power of the engines. Weight is the mass of the plane times acceleration, and lift and drag are proportional to velocity squared. At rest, the planes just sit with a normal and gravitational force. As the plane gets velocity, the plane will just stay underground as the lift and normal force compensate for the gravitational force. Thrust will be produced by the engine and the wing will incur drag. Liftoff occurs when the lift force is greater than the gravitational force, as the plane begins to accelerate upwards. Since lift force depends on velocity, there's a certain velocity until it lifts off. Let's say this is vt. We can simply calculate this takeoff velocity by doing some basic algebra. Now you might be asking, why did I just learn these 2 specific calculus concepts about estimation when I have rigid formulas for each of the key values? Here lies a problem. The only way to change velocity is to have a net force and acceleration. However, as velocity changes, so does acceleration, as drag is correlated to v squared. This relationship makes this one big loop, where velocity is a function of acceleration, but acceleration is a function of velocity. This means we have 2 dependent variables, and standard integration and differentiate cannot be applied. as you'll sometimes find it's not about exact answers, but estimations with minimal error. Here's a list of things we know. Acceleration is the derivative of velocity, and we know that at time t equals 0, velocity is also equal to 0. We also know that the integration of velocity is the change of x, or the change in position. We also know the acceleration given a velocity at a certain point, and thus we can estimate the velocity using Euler's method, as we always know what the acceleration is and we have a starting point. Recall, the acceleration is just the change in velocity. Remember, Euler's method only requires a starting point and a formula for the derivative, and we have both. We can then graph the velocity at certain time periods and then use integration. Recall, Riemann approximation only requires points on a graph, and since we already have points on a graph from our Euler method, we can then use Riemann approximation to find a change in position, or basically the runway length. Now, if we want a really small error, we will need a really small step length, and that could potentially mean that our step length is 1 over 10,000ths of a second or even smaller. That would be nearly impossible and extremely time-consuming to calculate by hand. However, we can always use Python to calculate this. This is a notebook I use to do the Euler method approximations and the Riemann approximations. So I first set up the variables of our plane. Our thrust is initially 300,000 newtons, our initial velocity is 0, our drag and lift are as follows. I will list out the airfoil I use and the surface area I use in the description. The gravity is the mass times the acceleration of gravity, and our mass is 220,128 kilograms. We set our time initially to 0. Our net acceleration is that formula, and we just set up sets so we can use it later to plot points. This code block performs the Euler's method. It keeps looping and changing the velocity according to the time until the lift is greater than gravity. This final code block does the final approximation for our runway needed for the plane to take off. This first block takes the Riemann approximation, and this second code block does an Euler method approximation. The Riemann approximation takes the perspective of velocity versus time graph, in which the area under the graph is the change in position. This for loop takes the perspective of a position versus time graph, in which velocity is the derivative, and since we know the velocity at certain points, we can approximate and see what the change in position is from a position versus time graph. If we run this code, we get 1334 for both Riemann and the Euler approximation methods. Thus, we can be confident that the length of runway needed is 1334 meters. And this is how fundamental calculus concepts are applied in fluid mechanics. Now, knowing the exact runway needed for this airplane to take off is not really necessary, as engineers will extend runways to build in redundancy in case for any pilot error. However, this should still give you a taste for how calculus is applied in a broader physical context. In fact, in the movie Hidden Figures, Euler's method is even mentioned explicitly to calculate changing orbital trajectories on the Apollo missions. Here's a clip.
The problem is when the capsule moves from an elliptical orbit to a parabolic orbit. There's no mathematical formula for that. As we can calculate launch and landing, but without this conversion, the capsule stays in orbit. We can't bring it back home.
Maybe we've been thinking about this all wrong.
How's that?
Maybe it's not new math at all.
It could be old math. Something that looks at the problem numerically and not theoretically. Math is always dependable.
For you, it is.
Euler's method.
Euler's method.
Yes,
That's ancient.
but it works. It works numerically.
That's it.
Let's type it up.
Even today, NASA continues to use Euler's method for its modeling code for thermal protection systems. In computer calculations, the exact values may not be necessary, especially since they could take up a lot of power, memory, and runtime. In fact, calculators don't display exact values. Instead, they display really good approximations for your sine and cosine values, and those approximations are usually polynomials derived from calculus. Sometimes, only a good approximation is needed to achieve the task at hand. Here are some interesting questions relating to the airplane problem. Pause and try to solve them. 1. What happens if we have some headwind? How about some tailwind? 2. How do you calculate the length of runway needed during touchdown? And 3. Aircraft carriers have shorter runways. How do military engineers compensate for the shorter runway? I would like to thank and shout out my high school calculus teacher, Ms. Cisnero, and Dr. Jeremy Keys, a professor in mechanical engineering at Northwestern University. This video would not have been possible without them.